Hi, my name is Jialin, and I'll be presenting our work on Tsunami, a learned multidimensional index for correlated data and skewed workloads. So the motivation behind Tsunami is that we want to improve the performance of scanning and filtering, which is a key step in processing analytics queries. And to explain what I mean by scanning and filtering, let's imagine that in your data warehouse, you have this simplified table with two columns, age and salary. Now, for illustrative purposes, we're going to visualize the rows of this table as points in multidimensional space. So here, the x-axis represents age, the y-axis represents salary, and every point represents a record in the original table. So now let's say a user wants to run this query. Compute some aggregation over all points where the age is between 40 and 50, and the salary is between 80 and 100K. So visually, the query's filter can be represented as this green rectangle, because the query needs to find all points inside the rectangle. And the most straightforward way to find those points is to do a full table scan over all the points. But this results in a lot of extra scanning over points that are not relevant, which I've shaded in red. And obviously, all this extra scanning increases query time and hurts performance. So one very common way for systems to reduce the amount of scanning is to sort the data by a certain dimension. So for example, if we sort all the points by age, we can avoid scanning any point whose age is not between 40 and 50. But the downside is that this doesn't help us filter over the salary dimension. So we still end up scanning a lot of extra data, which I've shaded in red. And of course, if we instead sort by salary, we end up with essentially the same problem. So instead of sorting by a single dimension, what we can do instead is sort based on a multidimensional grid. So for example, on the right, we have a grid with 6 vertical partitions over age and 5 horizontal partitions over salary, which when combined gives us a grid with 30 uniformly sized cells. Now, all points falling in the same cell are stored contiguously. So now we only scan the points in the cells that overlap with the green query rectangle. So essentially, this grid layout gives us the ability to filter by both dimensions simultaneously. Now, one major challenge with grid layouts is how to configure them, meaning which dimensions to include in the grid and also how many partitions to create in each dimension. So in our prior work, published in last year's SIGMOD, we introduced a learned multidimensional index called flood that is able to automatically adapt the layout of the grid for a particular query workload. So for example, let's say there's 2 users, each with their own workload labeled A and B. And here I've shown 2 queries sampled from each workload. Now workload A's queries are much more selective over the salary dimension than over the age dimension. And so flood would automatically create a grid that has many more partitions over salary than age, which minimizes scanning. Now, on the other hand, for workload B, flood would automatically create an entirely different grid specialized for just the queries in workload B. So this is the reason we call flood a learned multidimensional index, because it's able to learn the best grid layout for a specific query workload and dataset in order to minimize the amount of scanning. And this learned quality of flood is what allows it to outperform a lot of more traditional indexes and data layouts. Now, flood does have a couple practical limitations, which is what motivated us to create Tsunami. And one of those limitations is that flood can perform poorly if the query workload is skewed. So as an example, here I'm showing data with year on the x-axis and sales on the y-axis, and I'm showing a workload where every query is depicted as a green rectangle. So intuitively, this workload is skewed in 2 ways. First, it's skewed in terms of frequency, in the sense that the frequency of queries varies across this space, because queries appear more densely after 2019 than before. And this kind of temporal skewness is very common in practice because you're more likely to query recent data than stale data. And second, the workload is also skewed in terms of filter selectivity, in the sense that the per dimension filter selectivity of the average query varies across this space. So given this workload, flood would create a grid like this, which doesn't perform very well, as you can see visually by the fact that there's a lot of extra scanning of data outside the query rectangles. And fundamentally, the reason for this bad performance is that flood's single uniform grid can only optimize for the average query, which results in poor performance if the workload is not uniform. In other words, if the workload is skewed. So Tsunami, our new index, is able to adapt the query skew. And our key idea is to divide data space into disjoint regions so that within each region, the workload is not skewed. For example, here I've divided data space based on whether it's before or after 2019. Then each region gets its own independent grid that's specialized for only the queries that fall in that region. So now using Tsunami's layout, we're able to run this workload while scanning much less data than flood. So that's the core intuition behind how Tsunami deals with query skew. So now I'm going to make this intuition more concrete by presenting a simplified version of Tsunami's algorithm for finding the best layout. So starting with a full data set and a full query workload, the first step is to cluster queries into types that have similar selectivity characteristics. And to do that, we're going to generate a vector embedding for every query based on its filter selectivity in each dimension. So for example, this query here will have the two-dimensional vector embedding of 0.25, 0.06. And that's because the query's filter over year selects 25% of all the data, and the query's filter over sale selects 6% of all the data. And as another example, this tall, narrow query on the right would have a vector embedding of 0.02, 0.5. So every embedded query can be represented as a point in a two-dimensional embedded space. Now, the second step is to run a clustering algorithm, which in our example finds that there's two distinct clusters. And the final step is to then map these clusters back to the original space and assign query types. So the purpose of clustering is that now queries belonging to a specific type have low skew in terms of selectivity. So within each type, we only need to address skew in terms of frequency. Now the second step is to divide data space into disjoint regions to reduce query skew. So as I've written below, query skew is formally defined with respect to a certain dimension I over a certain query type in a certain range between A and B. So for example, let's say we want to find the skew with respect to the year dimension over the green query type between 2016 and 2020. So the first thing we need is the query density distribution, which I've shown here as a green curve. You'll notice that the curve is higher in areas where green queries are denser. The second thing we need is the uniform distribution over the same range, which I've shown as a dashed gray line. Now, by definition, the uniform distribution has no skew. So the skew of the green query type is computed as the distance between the two distributions, which you can intuitively visualize as the area of this blue region. So now we can compute skew independently for the purple queries. And since these are the only two query types in our workload, we sum the individual skews to find the total skew with respect to the year dimension is equal to 11. Now, if we were to divide data space into multiple regions, we could compute the skew for each query type in each region independently and sum them to compute the new total skew with respect to the year dimension. So now that you understand how query skew is computed, the second step of this optimization algorithm will essentially consider all possible ways to divide the data space, either along the year dimension or along the sales dimension, and it will pick the division that reduces total query skew the most. And one subtle point here is that Tsunami divides on at most one dimension at a time. So the search space of possible divisions scales linearly with the number of dimensions, not exponentially. Then the third step is to recursively apply step 2 in each resulting region until the query skew in each region is close to 0. And the final step is to simply create a grid in each region that's specialized for only the queries to fall in that region. So in our paper, you can find more details about the optimization algorithm and also details about how Tsunami deals with data correlations, which is another major contribution that I didn't have time to discuss in this talk. So in terms of results, here I'm showing two plots from benchmarking on two different data sets and workloads. The one on the left comes from New York City taxi rides, and the one on the right comes from performance monitoring data. We show query time on the y-axis, so lower is better, and I'm showing a different bar for every different index that we evaluated. And you'll notice that Tsunami, which is the rightmost bar in both plots, consistently has the lowest average query time. And that's mainly due to the fact that Tsunami scans much less data than the others. So now I'm going to add one more dimension to these results. Here I'm showing the exact same two data sets over the exact same indexes, again with query time on the y-axis, but now I've added index size on the x-axis, so it's better to be towards the left. And you'll notice that Tsunami, which is this blue dot, is lower and to the left of all other indexes. So overall, Tsunami is up to 10x faster and 100x smaller in index size than alternate 2 and traditional indexes. And it's also up to 6x faster and 8x smaller than our prior learned index, Flood. Some other results you can find in our paper are that Tsunami's advantage over other indexes scales with dataset size, selectivity, and dimensionality, and it's also adaptive to workload changes. So one thing to note, though, is that for all these experiments that I'm showing, we evaluated on workloads that do have query skew. But if the workload has no query skew, then Tsunami would perform more similarly to Flood, which is this orange dot in the plots. So in conclusion, scanning and filtering is a core part of query execution for analytics workloads, and Tsunami is a learned multidimensional index that can significantly reduce the overhead of scanning and filtering by automatically adapting the physical data layout to account for query skew and data correlations, which are both common in practice. So if you want to learn more about Tsunami and the other ML for systems work that we're doing at MIT, you can check out our blog. Thanks for listening.